So in the last video, we did the integral definition of the location of the center of mass, and I just want to make a connection back to the idea that that location of the equivalent force is driven by the requirement that the equivalent force gives you both equivalent force as of the distributed force and equivalent moment. Okay, and to show you that, I just want to show you how that works out for the case of center of mass and gravity, which is a simple case to see it for. So if I actually think about what the equivalent force is, right, the equivalent force for gravity, I'm simply going to integrate over the entire domain df, right? So I've got some object, right? It's got a bunch of chunks inside it. I'm asking the question, what's the sum of the forces on every single little chunk inside of that domain, right? And so when I actually write that integral out in a little bit more detail, right, I'm going to have minus rho times g times dv, right? Because rho times dv is a differential mass. This will be in the j hat direction, right? Assuming that that gravity is in the minus j hat direction, right? So my equivalent force, no, not as we found before, not surprisingly, is minus rho times g times j hat times the integral of dv, right? So that's what the equivalent force is. But let's actually ask a different question. What's the equivalent moment that is generated by the gravitational force in this case? Well, the equivalent moment here is simply going to be what the moment is that's generated by every single bit of gravitational force, right? So this bit of gravitational force, if this is my origin, is creating a moment of this r crossed with that f, right? This bit of force is creating a moment of this r crossed with that f, right? So my equivalent moment I could write as the integral of the domain of dm, right, which is just the differential bits of moment for each little piece of mass, which I could then go ahead and write in a little bit more detail as the integral of r cross, and what's my force? My force is the force that we actually already looked at here, right? It's r cross df. And if I write that out, I've got the integral of r cross rho times g times j hat with a negative sign dv. Right? But if I actually take a step back now and look at this integral at least, right? This integral, I could pull out the g and the j hat and the negative sign, or I could pull out the g and the j hat and the rho here, right? Those are all constants, right? So this is simply going to be the integral of r dv crossed with minus rho g j hat, right? And this should look pretty familiar, right? This is exactly the kind of expression that we're using when we calculate the center of mass, right? So in fact, this ends up, if I do a little bit more math here, this ends up being r com crossed with f equivalent. Okay, so by choosing the center of mass, we're actually achieving not only equal force, equivalent force of the distributed force, but also equivalent moment for the distributed force. Okay. Now the last thing I want to talk about is actually thinking about a different type of equivalent location, right? So we've talked so far about center of mass, which is one location that you place an equivalent force. Another place you'll often place equivalent forces are centers of pressure or centers of buoyancy. And this is particularly relevant for the project. buoyancy, right? Conceptually, this has to do with the idea that instead of thinking about a force that's distributed over the entire body as a contact force, so I have some pressure that's acting normal to the body at a variety of points around the body, and what I want to do is ask the question, what's the equivalent force and where does that equivalent force act? Well, I certainly could do an integral and do a bunch of calculation to try to figure out where is that equivalent force acting. That's kind of a pain, so I want to use a different approach to make an argument here, and it's an approach that sort of leverages some of the ideas that we talked about when we talked about free body diagrams. So here's what I want to do instead. I want to think about water that doesn't have a boat in it, and I want to think about choosing to cut out part of this water from the rest of the universe. And what I'm going to cut out actually is the piece of water that is the equivalent, that is the same shape and volume of what the boat displaces when you place the boat into the water. So I cut out some shape, and I'm going to call this my system, right? That chunk of water is my system. And then everything else is the rest of the universe, and this is my boundary, right? Well, if I think about that system, right, that system is at equilibrium, right? And since that system's at equilibrium, it must be the case that the sum of forces acting on the system is zero, and also that the sum of moments acting on the system is zero. Well, so, okay, let's think about what the forces and moments are acting on the system. The forces acting on the system, I've got two actually distributed forces acting on the system. One is a body force, right, which is due to gravity. So if I sort of draw my chunk of water here, I've got a gravitational force that's acting, right, which will be equal to the mass of the water times g in the minus j hat direction, right? And then I've also got some distributed force due to the pressure, right? And it must be the case that that equivalent force due to the pressure is equal to mg with regard to, because those are the only two forces acting, right? So the first thing I can claim, my first claim, is that F equivalent is equal to the volume displaced times the density of water times the gravitational force in the plus j hat direction, right? So that's the first claim I'll make, is that is what my equivalent force is going to be. And the reason that's my equivalent force is that is the magnitude of the gravitational force. It must be equal and opposite since the system's at equilibrium, since this chunk of water is not going anywhere. Or in the case of the boat, since the boat's not going anywhere. Okay? Now the second thing I need to ask about is, where does that force actually act? And the answer to the question, where does it act, has to do with requiring that the sum of moments be zero. Right? And the sum of moments has to be zero about any origin that I choose. Well, the most obvious place that will achieve that is actually to put the center of buoyancy at the center of mass of that chunk of water, right? Because if I choose that to be the location where the equivalent force of pressure is acting, or the buoyancy force is acting, right? Then I get a free body diagram that looks like this. I've got a gravitational force that's going down. I have a buoyancy or pressure force that's going up. They're equal and opposite. They're both acting at the same point. They clearly give me zero moment and zero force. Now, I could actually choose to put that buoyancy force anywhere along this line, right? There's not actually sufficient information for me to decide where I should put the buoyancy force other than somewhere along that line. But conceptually, it's sort of easiest to think about that buoyancy force as being located at the center of mass of the displaced water. Notice that is not the center of mass of the boat. Okay. So that's, I think, an easy way to think about where a center of pressure acts, at least in the case of sort of a static boat. In general, figuring out where the center of pressure is quite complicated. So, for example, if you think about what an airfoil looks like when an airfoil is traveling through the air, right? You've got some streamlines going on this. You have pressures acting in different directions on different points on this airfoil. And figuring out exactly where that equivalent force is actually really difficult, and is going to change depending on how what the attack angle of the airfoil is, what the speed of the air is, what the fluid is. You know, there's a lot of stuff that determines this. So in general, deciding where that equivalent force is not necessarily an easy thing to do, but in the static case of a boat sitting in water, it's a fairly straightforward thing to do.